welcome to NPTEL MOOC on fiber optic communication systems and techniques. In the previous module we were discussing the effect of fiber property called as dispersion. We will continue to discuss that dispersion because it is very important effect on signals that are propagating through the optical fiber. Okay. So, at the end of the previous module we said that I can think of or we can think of a fiber of certain length L as having a transfer function that would be in the frequency domain being represented as e power minus j beta 2 by 2 omega square z, or rather in this case, since the fiber has a length z equal to L, this would be the transfer function. Okay. So, if I know what is the Fourier transform of the pulse that has been launched into the fiber, then I can find out the Fourier transform of the same pulse at the output by multiplying the input Fourier transform, that is Fourier transform of the input pulse, with the transfer function, which of course is a function of the length L. Okay. This is the transfer function that we actually derived in the, or at least made it plausible in the previous module. Okay. And just to remind you, this capital omega is actually the frequency deviation, that is we are not really interested in knowing what is happening around the carrier frequency, because carrier frequency omega 0 and the carrier wave itself will propagate with what is called as the phase delay, and that really has no real importance for understanding the pulse propagation or in general optical signal propagation through the fiber. So, if we could set omega 0 equal to 0, that is we can set artificially omega 0 equal to 0, then we will be working in what is called as the baseband of the system. If you do not set omega naught equal to 0, then you will be working in what is called as the pass band or the band pass system. Okay. So, I am going to assume that omega 0 is equal to 0 and simplify or rewrite the notation. So, instead of using the capital omega, I will now use the small omega, which will then represent the baseband frequency. Of course, if you want to really know what is happening at the carrier frequency, you simply have to take the output Fourier transform and translate it again by omega 0 in order to translate the spectrum from the baseband to the pass band. Okay. So, I hope that this small change from pass band to baseband should not distract from the fact that the transfer function is actually a complex number. Okay. For a given value of L, it then depends on beta 2 and omega square, where omega is the frequency component, different frequency component of the pulse that has been launched into the optical fiber itself. Okay. Now, before we go ahead and understand different pulses and how they are affected by the dispersion parameter beta 2, let us derive what is called as a pulse propagation equation. Now, this derivation is not so mathematically rigorous. I do not want to focus too much on the math of this pulse propagation equation, but I do know that if I in general consider the Fourier transform of the pulse, okay, after it has propagated a distance z in the optical fiber, can be obtained as a 0 omega, which is of course the input Fourier transform of the pulse that is launched into the fiber at z equal to 0. This would be multiplied by the transfer function. Since I have removed beta 1 term from this transfer function, simply because I do know that the envelope, which is a of z t, would actually travel with the group velocity v g, and this beta 2, which is describing how the group velocity itself changes with respect to omega, is what is called as the group velocity dispersion, or sometimes called as group delay dispersion. Okay. These two terms are used synonymously. GVD is what I would call this term because it is kind of easy to remember. Okay. So, what this beta 2 is telling you, if you recall what beta 2 was, beta 2 by definition was the second derivative of beta with respect to omega, or it was the first derivative of beta with respect, or del beta by del omega. Del beta by del omega we have already seen to be equal to 1 by v g, okay, where v g is the group velocity, and therefore, what this beta 2 is telling you is how this group velocity itself is changing with respect to frequency. Okay. So, that is why this beta 2 is called as the group velocity dispersion parameter. So, as we have seen in the previous modules, we see that the carrier will move with a velocity Vph, the envelope will move with a velocity Vg, that is the center of the pulse will move with a velocity Vg, but then the pulse distortion that happens is because of this Vg not being a constant with respect to omega, but actually being varying with respect to omega. So, it could of course be considered equivalently as varying with respect to lambda, that is wavelength. So, sometimes that is also used. Okay. So, this of course is where we had seen in the last module. So, I know how to obtain the Fourier transform of the pulse which is propagating, and it has propagated a distance z and is subjected to dispersion beta 2. Therefore, this is how the Fourier transform would look like, right. Now, what if I actually differentiate this one with respect to z? Okay. So, if I differentiate this one with respect to z, of course, the first term is completely independent of z. So, it is a constant. So, it does not really get differentiated, it just gets multiplied. And when you differentiate this term, which is the exponential term with respect to z, it will pull out minus j beta 2 by 2 omega square. Please note that the differentiation is with respect to z and not with respect to omega. Okay. So, because I am differentiating this one with respect to z, I will pull out this minus j beta 2 by 2 omega square, and of course, since this is an exponential, I have to keep the remaining term the exponential as it is. And now, you quickly realize that this entire term a of 0 omega multiplied by the transfer function is simply the pulse at, or the Fourier transform of the pulse at z itself. So, what we have is a fairly simple linear equation which tells you that the derivative of the pulse Fourier transform at any point z in the fiber is directly proportional to the Fourier transform itself. Okay. So, this is what you actually get. So, this is a simple linear equation that you are going to get, and if I were to go back to time domain by taking the inverse Fourier transform, then I will obtain. So, I am now using the small a to denote that this is a Fourier, or rather the inverse Fourier transform of the capital A envelope. So, I have del A by del z, I have just taken the inverse Fourier transform of the previous expression, and this should be then equal to j beta 2 by 2 del square A. Of course, I have to use partial derivative because my pulse envelope A is actually dependent on z and t. Okay. So, this is what you obtain. Now, why did I write this as del square by del t square? Because in Fourier transform, del by del t corresponds to multiplication of the Fourier transform by j omega, and therefore, del square by del t square would be minus omega square, and because there was a minus omega square in the previous one, I replaced minus omega square by the operator del square by del t square. So, please take a look at this equation. This is very interesting, very important equation. There is only a couple, there is only an important point that I would like to make here. The time that we have written is not actually the time variable, but it is what is called as the delayed variable, or what is called as the retarded time. Okay. Retardation means delay, okay. And that retarded time is delayed, or the time is delayed by a factor of 1 by Vg. So, you recognize that z by Vg would be the delay that the center of the pulse would experience while propagating through the fiber with a velocity Vg, and we have simply taken the time reference to be on the center of the pulse, and therefore, the actual time that we are measuring around the pulse is not really the time with respect to a global coordinate system, but rather a time that is measured at the center. So, center is the one which we have taken to be the time reference, okay, and we are actually looking at that time. So, keep that in mind, and this z by Vg term, that is all coming off because of the fact that you have beta 1 which is non-zero. Okay. So, you have these pulses which are, because beta 1 is non-zero, the pulse center would travel with a velocity of Vg. Okay. So, having made that remark, okay, for now we will go ahead and forget about that remark, and let us see what kind of solution do we actually have for this pulse propagation equation. For that we need to consider some interesting pulse shapes. Okay. So, I am going to consider an important pulse shape in optical, in fiber optics community and in general in optics community, called as the Gaussian pulse, which is defined as e power minus. So, there could be some constant a 0, I do not really want to worry about the constant. I do not think you should also worry about the constant except when you are solving numerical problems with this one, but you concentrate on the shape of the pulse. So, notice that I have just written a of t, right. This is because I am actually going to send this pulse into the fiber where the fiber is located at z equal to 0. Okay. And notice how the exponential is, because there is a t square, the pulse is actually symmetric with respect to t equal to 0, because positive values of t will give you the same t square, negative values of t will also give you the same t square value. Because of the squaring, the sign has gone down. Okay. So, this is a pulse which is symmetric at t equal to 0. It also has its maximum at t equal to 0. What is the maximum value at t equal to 0? It will be equal to the constant a naught. Okay. And what happens as t goes off to infinity on both sides? Well, it is an exponential term with a minus sign out there, and therefore, as small t tends to become larger and larger, the amplitude of the pulse actually goes to 0. Truly it goes to 0 at only t equal to infinity. So, we call this as asymptotically going to infinity. Okay. So, this is the pulse that I am going to launch, and just for your reference, okay, this is how the pulse would actually look like. Of course, I cannot show you how it keeps going all the way to infinity. So, I am going to just draw it like this and then leave it, with the hope that you understand this pulse is actually going towards 0 as t tends to infinity. Okay. At t equal to 0, it has a value of a 0, but I am not going to plot this a of t. I am not going to plot this a of t, but rather I am going to plot magnitude a of t square. Of course, in this case magnitude does not really serve any purpose, because capital T 0 is actually a constant, a naught is a real constant we have assumed. So, we could as well have used the square of a, but in general we will see that after the pulse has propagated, the envelope actually becomes complex. Therefore, I am going to use magnitude square and I am going to plot the magnitude square. Okay. What is the significance of magnitude square? Well, what is the significance of a of t itself? The electric field itself at z equal to 0 will be given by a of t, which is the input pulse that you have launched, times e power j omega 0 t, correct. So, this is actually the pulse, or this is actually the electric field that is propagating in the fiber, and therefore, when you take the magnitude square, you are actually taking the magnitude square of the electric field, which we know from our discussion of Poynting vector to be associated with the power density, or if I also integrate it over the cross section, I will actually obtain the power. Equivalently, I can also think of power as intensity, because kind of they are related to each other, right. So, this is the significance of this pulse envelope. The square of the pulse envelope, except for some numerical factors that go into it, will represent the power or intensity of the pulse. So, when I square it up, when I take the magnitude square and square, the 2 in the denominator of the exponential function will go away. Okay. So, this will be a 0 square. Please remember, a 0 is a real constant, I have e power minus t square by t naught square. Now, if I plot this one, at the origin I have a 0 square, correct, which is where the pulse goes to its maximum, and then at t equal to capital T naught, right, at t equal to t naught, something interesting happens. So, let us say this is t naught, the pulse value would have dropped down to about 1 by e times a 0. Okay. So, again at minus t 0 also you would actually have 1 by e times a 0 square, and if you are not too fussy about defining the width of the pulse, you can consider this distance itself as the pulse width. So, you can consider this as the pulse width, which is about 2 times t naught. Okay. But in general you do not really consider 2 times t naught as the pulse width, because what you are looking for is not 1 by e, but what you are looking for is about half times a 0 square. So, the distance between 2 points where the power actually drops to half the power at the maximum, or half the peak power, is what is called as the pulse width, and this pulse width, which I will write this as TPW, will be approximately equal to 1.65 times T0. Okay. So, it is slightly smaller than 2 T naught, but this is what is normally used as the definition of pulse width, and this is called as FWHM pulse width. What does FWHM stand for? It stands for full width at half maximum. So, it is basically at the full width, that is the width of the pulse where the power has actually dropped down to half the peak power. Okay. So, the lesson for us to remember before understanding how to solve the pulse equation is to understand that if T0 changes for any reason, in the sense that if the overall pulse width changes, then you are actually changing the pulse width. It could be increasing or it could be decreasing. We will see that there are cases where the pulse width can reduce, but in most cases pulse width typically tends to increase. So, how do we know all this? I mean, we know all this by going and solving this particular equation. Okay. So, how do I go and solve this equation is to basically go back to the, so of course, instead of solving directly this equation, I will actually use something that I already know here, right, or rather I know something at this point. I am going to take the Fourier transform and then multiply by e power minus j beta 2 by 2 omega square z, okay, and I will then calculate what is the Fourier transform and then take the inverse Fourier transform to obtain A of z t. Okay. I could have solved this equation, okay, but instead of solving that equation or equivalently I know how the equation has come out. So, I am going to directly use that equation, which of course is the way of solving this equation itself. So, this equation that we have is actually the solution in the frequency domain of this equation. So, we are not really doing anything fussy out there. So, I am going to just write down that the pulse at z omega, maybe I should have used a capital A here, let me go back and use a capital A, is actually given by A of 0 omega, which is the Fourier transform of this A of t, multiplied by e power minus j beta 2 by 2 omega square z. What is the Fourier transform of a Gaussian pulse? I know that the Fourier transform of a Gaussian pulse is also Gaussian, but it is also important to know the expressions. Okay. So, roughly e power minus t square by 2 t 0 square. Please note that I am not actually transforming the power, I am only transforming the amplitude. Okay. So, this one will have Fourier transform which is like e to the power minus omega square, and because you actually had t 0 square in the denominator, this would be t 0 square, and there will be some additional factor out there, I think it would be by 2, and this is what you actually have for the Fourier transform. Okay. So, when you take this Fourier transform and multiply it to e to the power minus j beta 2 by 2 omega square z, what you will actually get as the Fourier transform of this one is e power minus omega square is a common thing. So, in fact, omega square by 2 seems to be common, I am going to remove that one. What I have is t 0 square plus j beta 2 times z. So, this is the pulse Fourier transform after it has propagated a distance of z. Now, if I take the inverse Fourier transform of this one, okay, I have to treat this entire t 0 square plus j beta 2 z as some t p square of z, okay, and of course, I know that this t p square of z is going to be complex because it is, there is a j term out there and there is a beta 2 term. Okay. So, when you take the inverse Fourier transform and write down the actual expression for A of z t, which I will leave as a small exercise to you, you will see that there will be a constant A 0, okay, and then there will be that constant multiplied by a term which is very interesting, which is beta 2 square z square divided by t 0 square of square. Okay. So, you might be confused as to why I am not writing t 0 to the power 4, but there is a reason why I am not writing, I will come to that reason very shortly. So, this is what you actually have. So, 1 plus beta 2 square z square by t 0 square of square. Okay. This is the amplitude of the pulse, that is of course, because there is a term that is sitting here, right. So, and this has to be inverted out there. So, I have to express that in terms of its magnitude and phase, and that is what I have actually done over here. And then you have e power minus t square by 2 t p square of z, okay. And again t is not really t, but t minus z by v g, you already know that. In addition to this, there will be another complex term that would be function of z and t as well. Okay. So, this is important to remember what is really this one, and if you actually look at what is phi of z t, that would be equal to kappa t square minus half tan inverse of beta 2 z divided by t 0 square. Okay. Do not worry how did you get these equations, you actually get these equations by fairly simple means of separating it out, writing a complex number in its magnitude and the phase form, and of course, this phi of z t that I have written where kappa is a constant is dependent on the time variable by t square term. So, it is a quadratic dependence on time minus some half tan inverse of beta 2 z by t 0 square, and this term that you have half tan inverse of beta 2 z by t 0 square is just a constant phase, of course constant only with respect to z. As long as you are looking at a particular point in z, this term will essentially be a constant, and this T p square of z is actually given by t 0 square 1 plus beta 2 square z square divided by t 0 square of square. Now, what is the significance of this term that is sitting inside? The significance of the term that is inside here beta 2 square z square by t 0 square of square is very interesting. Suppose I consider the situation where instead of writing this as beta 2 square z square by t 0 square, I am going to write this as magnitude of beta 2. Okay. I need some space here, so I am going to rewrite this. So, I will write this as magnitude of beta 2 z by t 0 square. Please remember t 0 is a real number, but beta 2 can be of two signs. Beta 2 can be greater than 0 or beta 2 can be less than 0. So, when beta 2 is greater than 0, we call this as normal dispersion. When beta 2 is less than 0, we call this as anomalous dispersion. Okay. Anomalous is simply opposite of normal. The reason why we call this will come out shortly, so do not worry about that. But because the sign of beta 2 can be positive or negative, it is common in fiber optic community to actually write this as sine of beta 2 multiplied to magnitude of beta 2. Okay. So, instead of writing sine of beta 2, I am going to simply use a variable s which denotes the sine of beta 2. If s could be either plus 1 or minus 1, plus 1 when beta 2 is greater than 0, minus 1 when beta 2 is less than 0, just to take into account that you have anomalous dispersion. So, I can write this term beta 2 square z square by t 0 square as beta 2 magnitude z by t 0 square. Of course, I can put an s here and then square the whole thing up, correct. But s can be either plus 1 or minus 1. So, square of s will be equal to always 1, and what I actually have is beta 2 square z square by t 0 square and can be written as magnitude of beta 2 z by t 0 square of the square term. Okay. Very interesting. Let me go ahead and call or denote this t 0 square by beta 2 as L d and call this L d as the dispersion length. Okay. So, what is this dispersion length? Dispersion length will tell you that when z becomes equal to L d, correct, when z is equal to L d, meaning when z is equal to t 0 square by magnitude of beta 2, which of course depends on what is the t 0 that you have given and what is the magnitude of beta 2 at that particular frequency. But when z is equal to t 0 square by beta 2, that is you have taken the fiber of length equal to L d, then the term in this square becomes equal to 1. Okay. So, under this condition this becomes equal to 1, and then T p square at L d, that is when you have propagated one dispersion length L d, will be equal to t 0 square times 2. Okay. I should have written 2 here, and please remember it is not t 0 square which is pulse width, it is t 0 which is pulse width. Similarly, T p square is the square of the pulse width, but T p will be the pulse width, which will be square root 2 times t 0, which means that the pulse has actually expanded, the pulse width has actually become increased by a factor of square root 2. Okay. And this factor of square root 2 increase and this distance L d is in the typical or in the paraxial optics approach is also called as the Rayleigh distance, which represents the amount of pulse or the transverse profile that is actually broadened as the light from the laser emerges out. So, we are going to see this we are going to see this Rayleigh distance or the Rayleigh length, or sometimes called as Rayleigh range, when we discuss the mode of a laser in some of the upcoming modules. Okay. But the basic idea is that when you propagate through a certain characteristic length, in this case the characteristic length happens to be equal to LD, then the pulse width would have changed by a factor of square root 2. Of course, I have kind of said that this is true for both normal and anomalous dispersion, but there is actually a difference in the way the pulse width actually goes forward, which we will see shortly. But before that, let me go back to this phase term phi, okay, and then look at what is the term out here. So, this kappa is a constant which you can find as a exercise, and when you actually understand that d phi by dt, right, when you fixed z and look at what is the derivative of phi with respect to t, this is actually equal to instantaneous frequency. Of course, in this case the instantaneous frequency is the frequency deviation that I am actually measuring. So, that you please remember, it is not really the actual frequency, but deviation of the frequency from omega 0, and that can be obtained by differentiating the phase, right. This is something that you know from your frequency modulation theories. Any derivative of phase will be the instantaneous frequency, and that derivative of the phase actually gives you, because the second term is constant, so that will go away with respect to the derivative, you will actually get 2 kappa t. It is very interesting that the instantaneous frequency deviation is actually dependent linearly on t, and kappa is greater than 0 for normal dispersion, okay, and it would be less than 0 for anomalous dispersion. Okay. Therefore, in the normal dispersion what happens, kappa sign is positive. So, what we actually is what we have is a positive slope, or sometimes called as up chirping. Chirping is a phenomenon wherein the phase of the pulse actually depends on the pulse time itself. So, across the pulse the phase actually changes, and for the case when kappa is less than 0, you have what is called as the down chirp. Okay. So, if you were to take this pulse, right, which is initially unchirped, and launch it over the fiber and wait for a large transmission distance, then what you actually see will be a pulse which has spread out. So, let us spread the pulse out, okay. But interestingly the pulse would actually have acquired a chirp which is linear and increasing across the pulse. The same situation for the anomalous dispersion regime would be that you actually have a pulse frequency which is very rapid initially, okay, and then kind of slows down. Okay. So, this chirp is the down chirp. So, the effect of dispersion onto the pulse that is propagating, which is initially unchirped and Gaussian, is to actually retain the Gaussian character, and in the absence of losses have the same energy as the input, but this pulse at the output would have broadened out mostly, and it would have also acquired chirp. Okay. So, this effect is not desirable, and mitigating this effect occupies a lot of interest in fiber optic communication system design, something that we are going to see in the future modules. Thank you very much.